next function we're going to look at is, as you can see, the square root function. So we need to just make sure that you're clear on the operation of square rooting. We spent some time last year dealing with numbers that were called radicals, which were basically just numbers that had square roots on them. Some of them were easier to work out than others. Root 9 and root 25, well, they're both perfect squares. They give whole number results. Ones like root 5 or root 7 or anything like that, it's not that they don't exist, it's not that they're difficult, it's just that they don't work out to nice whole numbers. So we can either leave them written in the radical form, root 5, or we can actually ask the calculator what the approximate value is. However, if at any time we are asked to find the square root of a negative number, what we say is that it has no real answer. Basically, in the real world, yeah. Now, that means that we need to focus on this. If you are asked to square root something, some number, it can only be done if the radicand, that is to say the number under the root, is positive. And if that radicand is negative, it cannot be done. Stated more algebraically, that means root x can be done if x is positive, greater than or equal to 0, and root negative x, you might be thinking, oh, that can't be done, that's negative. Yes, it can, if x itself is a negative number. Do some examples. If I were asked to find the root of x, and then let x be these two numbers, that's not a problem. Root 16 for root 8 doesn't work out to a whole number, but it doesn't matter, it exists. If, on the other hand, I let x be a negative number, then I'm going to run into problems. Can't do root negative 49, can't do root 2. Now, root negative x. This means first change the sign of x and then square root it. That's going to cause me to end up taking the root of negative 16 or the root of negative 8, and that's not going to happen. On the other hand, if I feed root negative x with numbers that are negative to start with, well, then I end up square rooting a positive number, which in the first case works out to 7, and the second one, 1.41. All good. Now here's another thing to think about, and it's not related to taking roots of negatives. It's related to the fact that anytime someone asks you what the square root of something is, you could actually respond by saying, well, which one? Because after all, every number has two square roots. Every positive number, that is, has two square roots, the positive one and the negative one. So if someone asks you to find a square root, then they should either say, give me either one, or they should specify which one they want in the first place. And here's where the notation is very important. The notation automatically specifies which root you're being asked for. Root 9 automatically, because there's no sign out in front here, means I want the positive one. Whereas if there's a negative out in front, it means I want the negative root of 9 in this case. So let's look at a few examples here. Negative root 25, does that negative cause problems? No. In fact, negative root 25, we're happy, that's just negative 5. Root 10, that means I want the positive root of 10, which is approximately 3.16. But root negative 1, can't do it. And even if I ask for negative root negative 1, it's not like these two negatives cancel each other out. We can't get past this part, so that doesn't exist. Now let's take this out for a test drive. Find negative root of x if x is 16 or 8. If I let x be those numbers, I end up getting the negative root of 16, negative 4, and the negative root of 8. Not a problem. However, if I let x be negative numbers and try to put those under the roots, well, I can't take the negative root of something that doesn't exist. Whether it's negative 49 or negative 2, it doesn't matter. So you guys, just go. if I want the negative root of negative x, and I'll let x be positive numbers? Well, if I follow the order of operations, I first have to change the sign of x. Once again, I end up having to take the root of something that's negative and then change its sign. Either way, it can't be done. So just get out. Now, what if I want the negative root of negative x, but this time I feed that expression with x's that are themselves negative? Well, the negative under the root arrives just in time to cancel out the negative that belongs to the x, and all is good. But notice the answers that I get are both negatives, because that's what we're being asked for. Alright, so let's bring all of this stuff together. The idea of what x can and can't be under the radical, as well as which root you're being asked for. So if you're asked to do root x, that means automatically you're being asked for the positive root of whatever this number is, and it'll only be possible for you to do it if x is positive. On the other hand, if you're being asked for negative root x, it means you're being asked for the negative root, and it'll only be possible for you to do it if the number under the root is positive. On the other hand, if you're asked for the root of negative x, you are being asked for the positive root of a number, and you'll only be able to figure it out if the number x is negative. And if you're being asked for the negative root of negative x, you're being asked for the negative root, and you'll only be able to work it out if the number you feed it for x is negative itself. Now let's have a look at the 4 different basic square root function graphs. This is what's unique about the square root function, is that there isn't just one basic one. Really, there are 4, and they are created using those 4 different radical notations. Let's look at this first one, the blue one. If I define my function to be root x, automatically there's only certain types of numbers that I can put for x. Positives. Now I happen to have chosen positive numbers that are perfect squares just to make my life easy. I could of course put an x of 2 and an x of 3, but why would I do that? I'm also being asked to find the positive square root of each of these numbers. So automatically all of my y's for this function are going to be positive. And if you were to graph that, this is more or less what it would look like. It's increasing, which makes sense. As x gets bigger, so does y, but it doesn't increase very quickly. Looking at the green graph, the next one, the negative root of negative x. Once again, I have to feed my function with positive x's in order for it to exist. And the fact that I've stuck a negative in front here means I'm asking for the negative root. So all of these y's will have to be negative. And that means in this graph, all of the ordered pairs have positive x's and negative y's, which means this is what it looks like. You can think of it actually as a reflection, a vertical reflection of this blue guy over here. Next function, root negative x. What kind of numbers do I have to feed that for my x? In order for it to work, it's got to be negatives. Once again, I picked nice numbers that work out to nice y values. I'm asking for the positive root of each of these though, so all my y's positive. So this function has ordered pairs that have negative x's and positive y's, which means it looks like this. Notice this one looks like a reflection of the blue guy in the y-axis. Last but not least, the purple one, negative root negative x. Once again, I have to feed that with negative x's in order to be able to take the root. And since I'm being asked for the negative root, all my y's are negative, which means this graph looks like this. There are your 4 basic square root function graphs. Notice the first one increases and goes to the right. The second one decreases and goes to the right. The red one, actually it decreases. If you look at it from left to right, it decreases, but its arrow points off to the left. And the purple one increases, again, if you look at it from left to right, but it's got an arrow that points off to the left. So here they all are put together on one graph. There's the first one, the green one, the red one, and the purple one. That's what they all are. Now, if we take two of these together at the same time, they form the inverse of the basic quadratic function. Which two curves would that be? Well, here's the basic quadratic function, and as you can see, it's these two guys right here. Root x and negative root x together form the inverse of y equals x squared, which means the red and the purple one must form the inverse of negative x squared. Interesting.